All right, so this is topic 3. We're looking at uniform motion and velocity. So the first thing we need to talk about is the difference between scalar and vector quantities. It says motion may be communicated in either a scalar or vector quantity. So what is really the difference? Well, the difference here is between quantities. So quantities that describe the magnitude of motion are referred to as scalar. So when we're talking about like how far, it's giving a size or an amount. So it's saying we went 5 kilometers from the school, a vehicle travels at a speed of 110 kilometers an hour. So it's telling you, I guess, a piece of information, a number, but it's not telling you any context to it. So on the other hand, vector quantities, those are ones that include direction. So when we're looking at these examples, it says a student lives 5 kilometers south of the school. So in our mind, we sort of have an idea of where that is. Like on a map, it's south, sort of gives us an idea. If we're just saying 5 kilometers, it really could be in any direction. So that's the major difference here between scalar quantities. So they're really just numbers. And vector quantities, these have a direction. They're a number and a direction. All right. So how we do this, it says recording direction. There's a couple different methods that we can use, and this first one is called the Cartesian method. It says one method of recording the direction that an object travels is the Cartesian method, or the x-axis method. So the positive x-axis is considered to be the beginning and is assigned an angle of 0. As you move counterclockwise, the angle increases and the direction of a vector A is 60 degrees. So what this is all saying here is that we consider right here, and maybe you can't see my yellow, but this line, that to be 0. And that's what it always would be on a graph. So we basically go from here all the way to the line and then figure out that's 60. So that vector is 60. Remember that in a right triangle, there's 90 degrees. So this 90 degrees would be this and this. So this whole part here is 90. So this line splits it, and we've got 30 on one side and 60 on the other. Another way of recording direction is using the navigator method. And basically this is probably used more commonly than the Cartesian method. I almost exclusively use the navigator method, but anyway, it says north is considered to be the beginning and is assigned an angle of 0. So north on this picture would be here. Okay, I can label that northeast, southwest. So as you move clockwise, the angles increase. So you're going clockwise from north this way, and it gets bigger and bigger. And that's something that most people use. You might hear people say like, oh, they did a 360 or they did a 180. You're literally using the navigator method to figure that out, where your starting point is where you are, and then where you stop, you find that amount of degrees or of that angle that you've moved, I guess, like away from the starting point. So if we were going to look at vector A here, which is that line that we've had in the last couple pictures, in order to figure that out, basically we start at north, which is at the very top, and we start to move clockwise to the right, in this case, right and down. And we basically calculate how much is between where we started and where we stopped. And if you were to be able to measure that, it would be 30 degrees. So how we would say this in a navigator method is that the vector A is 30 degrees east of north, or you could say it's 30 degrees E of N. So using that big E, big N in those square brackets, that's sort of how we sort of abbreviate those types of navigation or directions. All right. So I'm not too sure why, but it seems like I've already done this. Let's do practice number 1 here, and we're gonna do this on this picture and determine the direction or the angle of the vector for using the Cartesian method and then the navigator method. So if we look at that vector, vector B, the Cartesian method, remember is, in my drawings here, we're going from here all the way to it. So we actually go counterclockwise, and remember that this is 0. So we're going all the way over here to the line. And to do that, basically, I hope you know this, but if you don't, that's okay too. You'll know it now. This whole thing, if we were to go around the whole circle, make a circle, that is 360 degrees. And that's maybe something you should know. If we go from here to here, that's half of 360 degrees, which is 180 degrees. Okay, so when we're doing that in this question, we're going from here all the way to here is 180, and then from here to here is that extra that we need to add to the 180. Okay, and something we can figure out by looking at this picture is we know from here to here, I guess I should draw that as a circle, but that whole area is 90 degrees, right? And half of it is 65, so that will tell us, that'll help us to figure out the other side, and that's what I did here. So I did the 180, which is this, to the line, and then that little part is basically whatever this whole thing is 90 minus this 65. I know I've got a lot of lines here. I don't like, it looks very confusing. Yeah, so we're only literally looking at 180 is there. And then we are looking at this part. So to do that, we go 90 minus 65. Okay? And if we do 90 minus 65, it is 25. I sort of figured that out. So we got 80 plus 25 gives us 205. So from this line all the way over to here to vector B, it is 205 degrees, sorry. And then using the navigator method, we determine the direction basically as being we starting at, I guess, north, but really we're looking at it as in that sort of quadrant. So you're only with the navigator method looking at it in this sense. Okay, so that little quadrant you're looking at, and you're going to write down the number there, so 65 degrees, and then tell the direction that it's going. Well, we're going west of south. This is south, this is west. All right, so it's going in a southwest direction or west of south. I honestly don't even really care if you write southwest. It means the same thing. Okay? So practice number 2, it says an airplane reports its flight direction as 235 degrees. Which vector diagram correctly represents the plane's direction? So we're looking at just 235 degrees, so we know that they're using not the navigator method because there's no north, east, southwest. They're using the Cartesian method. So I'm going to write that here. I just need to be able to spell it. Cartesian. So this is the Cartesian method. And I find this one like almost, I don't know, I sort of like this one better, even though we normally use the navigator method. It makes sense to me because it's just like numbers, and I'm a numbers person. So what I did in this, and you can look at this if you're trying to figure this out. I'm not going to go through all of these. But what I did is remember in the Cartesian method, we're starting at this as being 0 and we're working our way around. Okay, and half of it is always 180, and then finding out that extra. So I got 180 plus 55 gives me that 235. So we're literally just figuring out from that right spot counterclockwise. All right, and that's what I did for all of them. So I've got my answers there. If we look, the question's asking us which one represents the flight direction of the plane that's going 235 degrees. And the answer is A. And that's because, yeah, we got that. When we used that Cartesian method, that's what we figured out. All right. So speed versus velocity. It says, although the terms speed and velocity are often used interchangeably, they actually refer to different measurements. This is something that I have a lot of trouble with. I will often refer to speed as velocity, but it's not necessarily. So there's a difference here, and it's not a huge difference, but the difference is scalar and vector quantities. So when we're looking at speed, it's a scalar quantity, and scalar, if you could go back a couple slides, that literally means it's just a number. Velocity is a vector quantity, and what that means is it's a number and a direction. Okay, so an example of a speed, well, I'm going 100 kilometers an hour in my car. Velocity, I would say I'm going 100 kilometers an hour north, for instance. I'm driving to Edmonton, so I am driving at a speed of 100, or a velocity, see, there's me mixing it up, but a velocity of 100 kilometers an hour north. All right, so that's that big difference there, and you can always refer back to this, but something to remember that normally in our life we would just be talking speed, unless you're really explaining well, but you might be like, oh, when I was driving to Edmonton, I drove 100 kilometers an hour. I guess that's sort of a velocity because you're telling us where you went, and if we know where you started, then we can figure out that direction, but really we normally just say speed in our daily lives. So here's an example, or just a little picture, sort of schematic to show you the difference between speed versus velocity. Velocity, on the other hand, here is something to consider, is that it can have negative quantities. So that negative or positive can also be used to mark which direction you're going. So back on the other slide up, I said I was going 100 kilometers per hour north. Another way that I could write that is writing 100 kilometers an hour and then putting a positive in front of it. So using positives or negatives, they basically denote what direction you're going. And a positive means you're going north or east, and a negative means you're going south or west. Okay? And where that comes from, sorry, I've not got a lot of space here, but where this comes from is looking at a plane, like a grid, where, or even just the northeast, southwest. If we're looking at this, everything that's going up is positive, down is negative, this side is positive, and this side is negative. So it lines up with what we know as being sort of positive and negative when we're looking at it on a plane or a graph. So calculating speed versus velocity, well, they actually literally are the same formula. The only difference here is that when we look at a velocity formula, we have a little arrow there. So this little thing is an arrow, and that's just telling us that we need a direction. So when we're talking about velocity is equal to distance over time, that distance has to have a direction in order for it to be a velocity. Without the direction, then it just becomes a speed, okay? So the literally same exact calculations, just using speed, using direction. Looking at distance, displacement, and position. Well, some more terms to learn, I guess, is the difference between distance and displacement. And I have a lot of, I guess students sometimes have a lot of trouble with this, but basically distance is, again, a scalar quantity. So this just means it's a number. So you say you went 50 kilometers, all right? When we're talking about displacement, on the other hand, that is a vector quantity. So this includes a direction. So it's a number and a direction. All right. So position, on the other hand, is a vector quantity that describes our specific point relative to where you started or your reference point. I'm going to explain this basically looking at this little picture. So displacement versus distance. If we were starting, I'm going to say right here. So if we started and we were deciding we were going to, I don't know, go from our house to a park nearby, let's say that. So that's X is our house. This is a park. There's basically two ways, I guess, you could go. You could take the path, and the path is going to bring you all along this winding stretch, sort of not really a straight route at all, but it'll bring you to the park. And you can go on an easy pathway to get to that park. So let's say this park is a little ways away, and if you were to walk there, it would take you, you would go, I don't know, 2.5 kilometers, let's say. So I'm going to say, that my distance is 2.5 kilometers. But if I was being lazy or whatever, adventurous, I guess, I could decide not to take the path. I could decide to cut through the woods. And by doing that, I make a way more direct route to where I'm trying to go. So when I'm talking about displacement, this is where I have a direct route. And let's say, I'm making this up, our direct route for our displacement is 1 kilometer. Right? So if we said how far from our house the park is, it really is 1 kilometer, right? And that's, I guess, sort of like how far it is, that direct point. So how far is it from where you started? That's your displacement. And our displacement is going to have a direction. So in this case, we are going down. So we are going to write south. Oops. If I can find my slide again. We're going to write south there. We could also write 1 kilometer with a negative sign in front. All right, so that's our displacement. Our distance, on the other hand, it's 2.5 kilometers. We took a lot longer route to get there, but that's our distance. So when we're calculating distance, we just are basically, and maybe that's on the next slide. Yeah, it is. Well, I won't get ahead of myself. There's a video there I will post. But in order to calculate these, I guess we're going to go over displacement first. Displacement is defined mathematically as the difference between two positions as shown below. So how we figure out displacement is basically we say, where did you start? And that's your number 1. And where did you end up? So where you end up, minus where you started will tell us what your displacement is. So your final or ending position minus your initial position will give us your displacement. So calculating the displacement, we can do this practice. It says Tommy walks along the pathway from his house to school each morning as shown by the diagram to the right. What is the total distance Tommy travels? So when we're talking about distance, we are talking about literally how far does he travel? How much meters or whatever does his feet take him? And the answer is, I guess, if he's going along this pathway, it would be 1,200 meters. And that's what I wrote right here. But his house, if we didn't take that path, is actually only 920 meters away. And you can see that with that arrow. So when we're looking at displacement, well, how far is he from where he started? He's 920 meters. And just to put that in perspective, our formula is D1, just kidding, D2 minus D1. So our D2 is where we end up, which is 920, minus where we started, which is 0. That gives us 920 meters, okay? So that's how we use that formula. We take where we end minus where we started. And in this case, it's literally the same. We're not starting at a different point, I guess you could say. So the next question is saying we're using the same picture, but Tommy walks the pathway from his house to the school and back each day, as shown in the diagram. So me writing this is actually not even right. This is perfect. I get to fix my mistakes from whenever I wrote this, like last year. It says, what's the total distance Tommy traveled? Well, we know he traveled to school and back, so it's not 100, it's not 1,200. That's times 2, right? Because we went there and then we came back. Our distance traveled was that times 2. So when we look at this, we would say we have 2,400 meters traveled. What is the total displacement of Tommy's daily walk? Well, this is where it gets sort of cool, or I think so, when it comes to displacement. Because he started here, he went here, and then he went back. So when we're looking at displacement, we are literally only looking at how far are you from where you started. Well, in this case, he's 0 meters from where he started. He started at his house and he ended his day at his house. His displacement was 0. He has not moved from where he started. And we know he has moved, but his displacement, how much has he displaced in direction? 0. Okay? And I make that example for myself as well. Like every day I get in my car, I drive to the school. I spend the day here and then I drive back and go back in the exact same parking spot. Well, if we looked at that as my displacement, it's 0. I didn't go any meters, I'm still back where I started. But if we're looking at distance, like what your car is going to say, it's going to say that you traveled more than 0 because your mileage is going to go up on your car because that would be measuring your distance. Okay, so displacement is literally how far you are from where you started, and distance is just that total distance that you traveled. An example here, and maybe I'll just try and do it again. This is A. It says an object travels 3 meters north. So as I'm reading through this question, I'm going to write down the pieces of information they gave us. I like to do that. Of its original position. It then turned around and travels 10 meters south. Only to turn around once again and travel another 2 meters north. So we're trying to figure out displacement. Something that's really going to help us here is by changing these letters, these north-south, two negatives and positives because that's going to help us just to easily put it in our calculator. So remember our north, east, south, west. We've got positives at the top, negatives. This is a negative and this is a positive. So when we're going north, it's positive. So I'm going to write 3 meters positive. 10 meters south, that's a negative. I'm going to write 10 meters. And then 2 meters north is a positive. So if I take those, add them together, 3 meters plus 2 meters is 5 meters minus 10. Our answer is going to be negative 5 meters. Or if we want to change that back, it's going to be 5 meters south. All right, so that is how you calculate that. Oops, I just did the displacement. I think that's actually B. Wasn't reading the question. But A is just finding our distance, and our distance here, we went 3 meters plus 10 meters plus, I don't know why this isn't working, 2 meters. So we would add all of that together, which gives us 15 meters. So distance doesn't require any sort of direction. So we don't need those negatives and positives, and that's what we'll just be basically adding up what we got there. Here's some calculating velocity questions. I will do, I guess, 1 or 2 of them for you, or maybe I'll just go through what I've got here. So the first question says, calculate the velocity of a vehicle that travels 30 kilometers north over a period of 0.45 hours. So when we're calculating velocity, we're using the formula V is equal to D over T. Then when we're doing this, we need to look through our question to find out what we got. Calculate the velocity of a vehicle that travels 30 kilometers north. So there's one piece of information over a period of 0.45 hours. This is going to be a distance, and this is going to be a time, and we are trying to calculate the velocity. So we're just going to plug these pieces of information into our formula. Velocity is equal to distance. Our distance is 30 kilometers. Oops. So 30 kilometers is our distance divided by our time, which we got as 0.45. We do that out in our calculator and we get 66.7. And then we need to make sure we're using our units. They're super important. They're going to be half of your points. So your units are going to be 66.7 kilometers an hour. So that kilometers an hour is your units. And that's what it is here. How do we know it's kilometers per hour? Well, we've got kilometers divided by, let's divide, and hours. So these just stay how they were in the question. Okay. You should also know that speed is measured in kilometers an hour, so that will give you a hint there. Okay. Number 2, it says a person walks at a velocity of 2 meters per second. So we've got a velocity here to a bus stop located 10 meters east away. So there's 2 pieces of information there. They've given us a velocity and they've given us a distance. We are looking for time. How long does it take him to get to the bus stop? Apparently I did this at the top here, so let's do this. So I did a little chart, I guess, of what I have. I've got velocity, I've got distance, and I'm missing time. We got to rearrange this formula, and I did post a formula sheet there for you that has these rearranged. But basically, what you need to do is you need to rearrange the formula so you get time by itself. And I'm not going to make you rearrange it. I'm just going to give it to you so it is there. So if we're looking for time, it's equal to distance divided by velocity. So we take our distance and divide it by velocity. Our distance is 10 meters east divided by our velocity, which is 2 meters per second. 10 divided by 2 gives us 5. We're looking for a time here, so are measured in seconds. Sometimes if you get confused with like how these units are canceling and so. Just remember that, well, it's a time, it must be in seconds, okay? You're not gonna have a time that is kilometers an hour. You're not gonna have a time that is meters, something like that. All right, now there's one more here at the bottom. It says a car travels at a velocity of 100 kilometers an hour north for a period of 2.5 hours. So here we've got a velocity and we've got a time. So our distance is what we're missing. So we take, rearrange our formula so that we have distance by itself. Distance is equal to velocity times time. We multiply our velocity, which is 100, by our time, which is 2.5. It's really kind of important that I put the units here. So if we do that, we go 100 times 2.5 and we get 250 kilometers. This is a distance, that's why we're in kilometers. Okay. Like speed, velocity can be represented with a displacement time graph or a velocity time graph. Here is some examples of how this might look. When we're looking at constant velocity, something is going to be going at the same pace. It'll actually look like a flat line on our graph. If we're looking at something that is accelerating, it's going faster over time, then it's going to have a upward slope. Downward slope if it's slowing down, okay? So these objects are both moving in the positive direction. However, an object A is speeding up while object B is slowing down. So you see speeding up, slowing down, okay? These objects are both moving in a negative direction. However, object C is slowing down while object D is speeding up. So when we're below the negative, we're slowing down, speeding up. Okay? So that is all that we have for that section. There is an assignment for you to do that corresponds to this, and it's on the Google Classroom. Please try that out and let me know if you have any questions. Have a great day.